Welcome. We will today for a couple of hours we will talk about another issue in satellite communication. The satellite medium is the physical layer. Now the effect of the physical layer on the higher layers, that's the main issue of the discussion today. Now we will take the higher layer as our regular user friendly system, what we all of us use, that is internet. And internet mainly is based on the transport layer protocol TCP and the protocol IP. So on TCP IP, which are higher layer than the physical layer, what is the effect of the physical layer on that? And that is what will be discussed today. So let's see. What will be covered is the first, those who are already familiar with TCP IP, for them it is just repetition, but many of you may not know, and we need not go into the details of TCP IP. We will see the effect in terms of delivery of data integrity and in terms of throughput that can be maximum achieved. So from that angle we will see the basic functions of IP and basic functions of TCP, and mainly the throughput is controlled using flow control in the TCP. So flow control and congestion control in TCP. Some of the terms which are coming unfamiliar, you have to get acquainted with that, like congestion control, flow control and congestion control in TCP. And of course the characteristics of the satellite medium, which we all know, but we'll see their impact on the TCP flow control protocol. And of course because there is some impact, there has to be some mitigation techniques. So the mitigations which are proposed to reduce this impact, that's what is the main discussion today. If we look at the characteristics of the satellite as a physical layer, one thing we have by now we are very familiar, it has a long delay, because satellite is a repeater which is high above the Earth atmosphere if communication through the Earth, and if it is between the planets or other satellites, it's always a long delay. That's actually distance is a big advantage of the satellite communication, but it provides a long delay. Now the other thing is error prone. Because of this long delay, we know that the power which is received at the receiver is very low, very weak, and we cannot transmit very large power from the satellite type of probes where the source of power is limited. So therefore you work at low C by N, so therefore the error is obvious, error prone. In addition, on the ground system there will be lot of multipath. It's a wireless link, so other interferences that may come in, so it's error prone link. Asymmetric channel bandwidth, obviously this is very common to our use, that is we like say in internet browsing we ask for a lot of information, but we are asking with a short query, so the uplink and downlink bandwidths are always asymmetric. That happens in most of the cases in satellite communication, so it's a asymmetric channel bandwidth. And of course it's limited link capacity, as we have seen in terms of error prone link. I mentioned that the power and the bandwidth compared to the terrestrial channel, it's limited, so it's a capacity in the satellite channel is a limited link capacity in terms of power and bandwidth. And intermittent connection, this is also another thing which doesn't happen always in other communication system, is let's say a satellite probe is orbiting the moon, and from the Earth somebody another Earth station is trying to communicate. So when it goes behind the moon, this communication is broken. It can happen in atmosphere also at higher frequency range. We have seen in Ka band and higher up bands when we communicate. In troposphere, if it's rain absorbs the energy, and obviously the link goes down. So connection is intermittent. That is another problem in the another characteristics of the satellite physical layer. Now with these characteristics in mind, let us look at what is the IP protocol and TCP protocol they do and how they work. mainly we are communicating with certain application. So, this application data is formatted in a higher layer, that is at the TCP layer, and the data is segmented, and the maximum segmentation is possible. TCP, they have defined certain maximum segmentation, we call it maximum segment size, MSS. This term MSS may come during our discussion. So, this is either segment size or maximum segment size. It is called TCP segment. You see the words which are used, the datagram, packets, frames. So, here they are called TCP segments. Now, when it's segmented, that segment is to be sent to whom and who is sending, and any other information that goes as a header. So, TCP as a header, and it is standardized that TCP header is roughly about 20 bytes of information. Now, with this TCP information, our TCP segment is passed on to the lower layer, which is IP, Internet Protocol. This IP, they call it datagram, like telegram, which is obsolete now. So, they call it datagram, or sometimes IP packet. They also add certain header. They have certain some functions to perform. So, for that a different type of header which is added, which is also of the order of 20 bytes. So, now the IP datagram looks as a, after the header, it looks as a rest of the things as a data. That data contains the header of the TCP segment and the segment, and that data contains the actual data. It is like that. Then this IP layer is going through the physical layer. So, it will pass on to the medium access control, that is that satellite medium access control, which is, we have seen that medium access control are FDMA, TDMA, CDMA, many other things are there. So, that medium access control MAC frame also adds some header. We have discussed this one earlier, that like CR, BTR, then Unicode and many other things they add. So, that is also adding a header, and sometimes they add a trailer also. So, it is enveloped. So, how they are enveloped, actual data is segmented and it is enveloped by TCP header, then it is enveloped by IP datagram, then it is enveloped by MAC frame. So, this is how the data is getting enveloped at different layer, and each layer performs based on that header and trailer information its own function. Now, what is the IP datagram characteristics? Very briefly we will touch that. What is the characteristics? It is simple and robust. It's very simple, and because of its simplicity it is connectionless. That is very surprising. It is a datagram, telegram, like telegram, it is datagram. So, it does not maintain the connection in future, what is to be maintained and all this. It is just one simple packet which is called datagram, will be simply delivered. It does not know whether previous to that another packet which was linked to this, information was linked to this, was sent to this destination, or this particular source has sent, or in future it has to be sent. It does not maintain that. So, it is connectionless, there is no connection, just one simple packet or datagram has to be delivered to a location. And so, there is no packet sequencing. Each packets are not sequenced at the IP level. Is not packet sequencing is not maintained at IP level, remember. And it says that it is a best effort. What is best effort? Best effort is delivery to the correct address. So, the address they maintain properly, the source and destination addresses are properly maintained. There should not be, it does not tolerate any error in that, but packet drops are possible, it may get missed. So, it does not care, IP protocol does not care if it is dropped. It does not care if the delivery is not in order, means first packet, there may be 10 packets going from one source to destination, since it does not maintain any sequence number. So, if the fourth packet has gone to some other router and it got delayed, and third packet and fifth packet has been delivered, and then the fourth packet arrives. So, 3, 5, 4 and then 6, 7, 8 it is coming like that. It does not care because it does not maintain sequence. So, it is possible that delivery is not in order. So, that is what is called best effort, and then it is unreliable, very surprising. It is unreliable because the data part is not protected. Data part error protection is not there, it just says so many bytes are data, header is protected. So, let us look at the there is the format of the datagram. In the IP datagram, the format, it is spread over 32 bits each of the line, each of the row. Here it is shown like this. So, there are many fields which are there. Look at this, there are source IP address and destination IP address, which is the part of the header. This is the header, first few 32 bits. This header has a checksum. So, only header has a checksum. Subsequently, there are data is not protected. So, header is well protected. So, it delivered the correct address. And then of course, there are other informations like what is the total length, that is after the header how much is the data. So, the total length could be variable, that is why they have put a field. So, there is a total length field. There are other fields are there, which is version number, header length. Header may be some options may be there, with that header length can be increased, the type of service, and then identification, whether it is a priority packet or ordinary packet. There are different flags. There are time to leave, TTL is time to leave, like that it is there, the options and paddings and data is there. But this is very important, that there is a source IP address, destination IP address, and there is a header checksum for that. Okay. And let us see what is the TCP, which is next higher layer, what is their format. The TCP segment, now it is called segment, TCP segment format is also extended 32 bits and each rows are shown. Here is a source port and destination port addresses are given, and it maintains a sequence number. So, it will provide the connections, it will provide the orderly delivery. There is the acknowledgement number based on that sequence number from the receiver to the transmitter. So, there is a field of acknowledgement, and there is a checksum. This checksum is protecting the header as well as the data. So, it is reliable in this case, and other options are like there, urgent pointer and very urgent flag, ACK flag, and many other different flags are there. We need not be interested on that, but there is something called window. We will come to this window thing, we will try to understand what is that, and there will be discussion on that. Okay. So, this is the TCP segment. So, what is the characteristics of the TCP? That is, it is connection oriented, because it maintains the addresses of who is sending to whom. Port addresses are maintained, and then sequence number is also maintained. So, therefore, it will deliver in order in proper sequence that the receiver and transmitter will know in which sequence, which segment is to be placed where in the memory. And then it is reliable, because it is protecting header and data, both are error protected, and it is a full duplex. Therefore, the data delivery is ensured. In full duplex, the acknowledgement come when the once the data reaches and checksum is checked properly, it is correct, then the acknowledgement comes. So, data delivery is ensured, and there is a flow control. This is important, that the throughput they try to maintain to the maximum possible throughput that can go through a particular link. Transmitter attempts to match the network and receiver capacity. We will discuss this one, because flow control is a major issue what we will discuss today. Let us see how the ACK based communication takes place. It is very simple. There is a segment, as per the segment size there is a sequence number. Let us say sequence number n for this segment is being sent by transmitter. Sequence number n is going. I am not showing the delay properly. Say this y axis is the delay. So, after some time the sequence number n is acknowledged, that up to sequence n is this meaning of the acknowledgement is very important for the TCP, those who want to understand. Actually, what goes is send me the sequence number n plus 1, or actually instead of sequence, they in true sense they are asking for the next byte. It gives a byte count and the byte number. So, up to this byte I have received properly, give me the next byte. So, the next byte number will go, but for our understanding we will say this is the acknowledgement up to n. So, nth sequence is acknowledge n, but actually send the sequence number n plus 1, that is the message which goes. Okay. So, this is how it goes, but let us see a very simple way of, let us look at it. D is the channel delay. Let us say this is the channel delay including the processing, and then the RTT is a round trip delay including that is 2 times D, which includes the processing of the receiver, that is by the time it recognize and send the acknowledgement. So, the throughput is the segment size divided by RTT, that is the throughput. Now look at it. In satellite, the RTT will be high. It is of the order of quarter of a second, or maybe half of a second. It depends on where the satellite is, but it is quite high. So, since the RTT denominator is high, throughput will go low. So, as the satellite distance is more and more from between transmitter and receiver, throughput goes down. It is a major problem for us. Okay. So, channel capacity remains underutilized. See, a satellite channel has a large bandwidth. Let us say a good amount of bandwidth is given, but because of the RTT and the segment size, limited segment size, the whole thing remains underutilized, because it has to send the segment, next segment, after it gets the request that send me the next segment. So, this much delay during that time, the buffer sequence number n is waiting, and subsequent sequences are not going up. Now, let us say what happens if the sequence is lost. Say due to some error, receiver did not get it. So, after expected RTT, acknowledgement is not received after RTT due to the error, or maybe receiver buffer is already overflowing, or maybe the route delay is much more than expected RTT. Acknowledgement has not been received. So, what transmitter will do? It will retransmit. It will retransmit the sequence number n, and this retransmission, there is a timer for once you send a segment, you start a timer, and when this retransmission timer fires, and then it will be retransmitting. So, it is stated here, retransmission timeout RTO is larger than the expected RTO. There is a method of calculating retransmission timeout. We need not go into that detail of that. Okay. So, after certain timeout, it will retransmit. Fine. Now, so the lost segment is lost is detected by what method? By detected by the acknowledgement is missing. Acknowledgement did not come within certain time. So, that is how the segment is lost. Transmitter will come to know the segment is lost, because there is a missing ACK, and transmit buffer has to hold that sequence number n until the acknowledgement for that is received. So, transmit buffer has to hold. So, these are the two learning of this retransmission mechanism. Let us say what happens subsequently. Sequence number n is sent, and the receiver send the acknowledgement of n, that is send sequence number n plus 1. So, the network capacity is the bytes per second into normally instead of bits per second in TCP at this layer people talk in terms of bytes. So, it is bytes per second into RTT, that is the network capacity. Now, that means that many bytes are possible to be kept in the flight. So, transmit buffer can be of that size, which is network capacity. So, transmit buffer approximately can be up to network capacity. So, throughput is number of bytes I can put in flight divided by the delay. So, I can go on pumping. What happens instead of waiting for the first acknowledgement to come, or nth acknowledgement comes, and then sending n plus 1, I go on sending the n plus 1, let it be in flight. So, that way throughput can be increased. So, number of bytes in the flight, which is a large based on the RTT and the segment size. So, number of bytes in flight divided by the delay, that is the RTT. So, throughput can be increased. So, what we can put, that transmit buffer can be put, we can call it a window. Now, the term window comes. Transmit buffer can be called a window, and which the window contains many segments. Here are numbered 1, 2, 3, 4, 5, 6 like that. It will have multiple segments. And this window, depending on the size of the network capacity or the RTT and at what rate we are sending, the window can have so many segments. And once the acknowledgement of the first one, which has gone at first received, then window can shift a little, because network in the network second, third, fourth are still on the fly. Only the first has been received. So, I can the first has gone out of the network. So, network is empty by one segment, I can push next segment, that is 6. So, transmit of each segment, of course, there is one thing you have to remember, each segment is lost, what will happen. So, for each segment separate RTO has to be fired, separate RTO has to be starts, and then segments are held till the acknowledgement for that segment is received. If it is not received, then of course that has to be retransmitted. That is why those segments are already sent, many segments are already sent, for each of them they have to be held, and each of them separate RTO has to be started. Okay. The transmit pointer will slide when the acknowledgement for the earlier segment has been received, that when the number 1 has received, it will slide to 6. So, now it will have 2, 3, 4, 5, 6, then 2 acknowledgement is received, which has gone out of the network, gone to the receive buffer. So, then 3, 4, 5, 6, 7, so it slides one more. So, like that it will slide. It is called sliding window arrangement. This is what is done in TCP. So, that window size is very important, that you remember the field window. So, window size is important. Now, if RTO expires for any one of the segment, that means ACK is not received for that segment, then that segment has to be retransmitted, but window will not slide. This is another protection they have provided, that window should not slide, and because we are not sure that network is overflowing or not. So, if ACK is not received, so that particular segment will be retransmitted, and it is assumed the network capacity is full in that, and window will not slide until the acknowledgement of another one received. Acknowledgement receivement, it has come out of the network and receiver buffer has accepted it. So, window will not slide at that place. So, this is sliding window. Let us see that some segments are already flying, what happens to them. So, sequence n has lost. We have sent the sequence n minus 1 as per the sliding window arrangement. We have already network capacity, we went on sending, n plus 1 has been sent, and acknowledgement for the since the n has not been received, receiver did not receive the n, but it receives n plus 1. So, instead of sending that n plus 1 has been received and send n plus 2, he has not received n. If you remember, we said acknowledgement means up to that has been received correctly. So, he cannot send the acknowledgement of for n plus 1. In that case, it says that up to n plus 1 I have received everything. Actually, he has not received n. So, then he will continue to say that send me send me sequence number n, send me sequence number n. That means, he is acknowledging the previous segment. Up to previous segment I have received, which is n minus 1, and n I have not received. So, send me n, though he has received n plus 1. Okay. So, this is a duplicate ACK. Earlier he has sent already that ACK n minus 1 already sent, that is why sequence n has gone, but which is lost. So, this is a duplicate ACK. Another segment has been received by receiver, which is n plus 2, still he will send me sequence number n, ACK for n minus 1 is gone. Another one still. So, like that you go on, receiver go on sending duplicate ACKs and continuously trying to send a reminder to transmitter that I have not received sequence number n, which is a gap in my receive buffer. There is a hole in my receive buffer, but these duplicate ACKs are telling some more things, that I have received subsequent 3 segments, may not be subsequent, I have received 3 more segments. Okay. So, 3 more segments have gone out of the network, out of the network, it has been received at the receive buffer. So, there are 2 meanings which are coming out of that. So, meaning of receiver continue, meaning that receiver is continued to ask for the missing segment, that I still do not have that particular segment, and for each correctly received segment after the missing segment it is sending the request. So, that after that I have received so many, as many duplicate ACKs come, segment number he does not say, but I have received so many segments. So, 2 informations are going out of this. Now, let us see the control of this transmit window is very important. That is because the source size is n times the MSS, that is maximum segment size, divided by RTT, that is actually nothing but the W by RTT, in actually it is in bytes per second, though I have written small b, so it should be meant as bytes per second. In satellite link RTT is large. So, W also could be large to maintain the same source rate or throughput. I can maintain RTT is large, I can make W large. But then the problem is TCP header window count size is 16 bits, that means 2 to the power 16 bytes is the maximum window size TCP header says. if you remember the TCP header format, it says so. Let us go back here. This is 16 bits. 16 bits means 2 to the power 16, that is the window size. 2 to the power 16 bits, bytes, 2 to the power 16 bytes is the maximum window size. That is possible. So, therefore, in RTT we have to maintain the source rate, RTT is large, W could be large, but it is limited to 16 bits. So, therefore, maximum window size is 2 to the power 16 bytes, and in case of satellite this may not be enough. So, you have to scale up. So, window size can be scaled up, there is an option. So, there is a provision of window size scaling option that is to be activated in case of satellite link, which is large RTT link. Okay. So, since time is up, we will continue the discussion in the next period. Thank you.